Today's calculus class is going to start us off with the first real strategy here for integration. So we should get started here, and we are going to be started with a man named Euler. So Leonard Euler, who we saw previously, was a Swiss mathematician, physicist, astronomer, geographer, logician, and engineer. I mean, the man did everything. Who made important and influential discoveries in many branches of mathematics, such as infinitesimal calculus and graph theory, while also making pioneering contributions to several branches like topology and analytic number theory. Again, those are things that you would do in college. That's the kind of math that you go to. He also introduced much of the modern mathematical terminology of notation, particularly in mathematical analysis, such as the notation of the mathematical function. He is known for his work in mechanics, fluid dynamics, optics, astronomy, and music theory. Euler was one of the most eminent mathematicians of the 18th century and is held to be one of the greatest in history. He is widely considered to be the most prolific, and his collected works fill 92 volumes, more than anyone else in the field. He spent most of his adult life in St. Petersburg, Russia, and in Berlin, then the capital of Prussia. So we talked a little bit about Euler last time. We had Euler's method, and of course we probably should give him the proper introduction, or the introduction that he deserves. Not that this lesson is going to be about Euler's method again, because it's not. So, the family of all antiderivatives, f of x, is the indefinite integral of f with respect to x. And that's denoted by the integral of f of x. So, if f is any function and f prime is equal to f, then the antiderivative of f of x is going to be that antiderivative plus the constant c. That's kind of review of where we were last section, especially if I'm remembering correctly, section 7.1. So for this problem, all we need to do is find the antiderivative of 2x minus cosine x. Not that big a deal, just x squared minus sine x plus c. Hopefully that kind of a thing is really easy for you at this point. Next, we have a reminder of the most basic integrals, including the constant multiplication of a function, the sum and difference of two functions, how do we deal with power functions, how do we deal with 1 over x or 1 over u, how do we deal with the most basic trig functions and the most basic logarithm functions. One thing you might notice in all of these, starting over at power functions, is we're not taking the antiderivative with respect to x. So some of you probably noticed in the last section that we have u to the n power du and not x to the n power dx. And then down over here we have cosine of u and sine of u. And that was done really on purpose. There's a reason for that. And the reason is that u is what we're calling our dummy variable. It could be anything. It could be x, it could be y, it could be t. In some instances, maybe you'll see it even as n. So we can substitute into u whatever we need to. Again, I'll say that again because that's a kind of a great one. We can substitute anything we want into u and take the integral with respect to u. The other thing to notice is that there is no product or quotient rule for integrals. So I always say this in class, and it's really important that if you are integrating a product, two things multiplied with each other, two functions multiplied, and you have a rule for it and you do something, you're doing it wrong. There is no product rule for integrals. Same thing with quotients. If you see one function on top of another function and you integrate it without doing another, I don't know how you would integrate it. Usually students would do the numerator function, the integral of the numerator over the integral of the denominator. That's totally wrong. There is no integral rule for quotients. So be aware of that, and if you catch yourself, doing that, then, you've just saved yourself a mistake. So for our exploration, we're going to talk a little bit more about that dummy variable. For these three functions, we're going to say f of x is x cubed plus 1. And we're going to say that u is equal to x squared. So we're going to find the antiderivatives in terms of x. The hint here is to make sure that the variable of integration matches with the variable in the function. In this case, everything should be in terms of x. In part A, we have f of x and dx, so that matches. Part A, we have integral of f of x dx is the same thing as x cubed plus 1 dx. And no tricks, that's really equal to 1/4 x to the 4th power plus x plus c. Part B, again we have f of u and du, so that's not a mismatch. The integral of f of u is the integral of u cubed plus 1, which is just 1/4 u to the 4th plus u plus c. But we want to do this in terms of x, so yeah, let's substitute we know that x, so u is equal to x squared, and that gives us 1/4 x to the 8th power plus x squared plus c, making the substitution that u is x squared. For part C, we get f of u dx, and we notice immediately that those two don't match. So let's start by just substituting in for u into the f of x equation. Then we're going to substitute because we know that u is x squared. And that's pretty easy to find the antiderivative of. So let's find the antiderivative of x to the 6 plus 1. That gives me 1/7 x to the 7th power plus constant. But that's not the only way to arrive at 1/7 x to the 7th power plus c. What if instead of turning everything in terms of x, we turned everything in terms of u? We'll start with u being x squared. That leads us to du dx is 2x, which brings us to dx equals du over 2x. Now, I have to turn everything in terms of u, otherwise I can't integrate. So if u is x squared, that means x is the square root of u. That's going to simplify to du over 2 root u, or 1/2 u to the negative 1/2 power. Now my integral of fu dx, that's going to simplify into u cubed plus 1 multiplied by the 1/2 of u to the negative 1/2 du. Now I'm going to distribute that all in there and then use the power rule to integrate. Finally, we know that u is x squared. So when I substitute x squared for u, I get 1/7 x to the 7th power plus x plus c. Wow, that was so much longer, even though we got to the same answer. All of which leaves us with a conclusion that the choice to substitute can drastically affect the outcome or the process of an integral. If you do everything correctly, you'll still get the same antiderivative, if you can get to the same antiderivative, but the path you take could be easier or more difficult. So we're going to keep that in mind, and as we make substitutions for u, we're going to make substitutions for u that make the integral easier. That's the point, is we want to make the integrals easier. So let's take a look at the next section here. So that preceding example implies that clever substitution can be used to simplify some integrals or make some integrals a nightmare. Now this isn't a product rule, but products where one factor is the derivative of the other can be simplified using something called the substitution method. So we're looking at this problem. Find the antiderivative of 3x squared multiplied by the quantity of x cubed plus 1 to the 4th power. We notice here that the derivative of x cubed plus 1 is 3x squared. And this tells us that a good choice here is u is x cubed plus 1. So if we say u is x cubed plus 1, let's do the same kind of thing that we did previously. So if u is x cubed plus 1, du dx is 3x squared. With a little bit of algebra, we see that du is 3x squared dx. So we can regroup things here in our integral. So we're going to rearrange. We're going to put this 3x squared together with dx. And then we notice that we have the x cubed plus 1. Then we take a look at what we had just previously written, and we notice that we can substitute x cubed plus 1 for u. So that's what we're going to do. Instead of x cubed plus 1 to the 4th, we make that u to the 4th power. We also notice that du is the same thing as 3x squared dx. So we can substitute 3x squared dx with du. So using that substitution, look how much easier that integral has become. I mean, u to the 4th power du, that's nothing at all. We know how to do that. That's just 1/5 u to the 5th power plus constant. And then now we can substitute back because we knew what u was to begin with. We knew that u was x cubed plus 1. So the antiderivative here is 1/5 x cubed plus 1 to the 5th power plus constant. See? Didn't make a mess this time. In fact, we made things easier. So let's take a look at this next problem, and we're going to see how do we make wise choices for u so that our integral becomes easier. So clue number 1, both the integrand and x cubed, or contains both x cubed and x squared power, and there's only a difference of 1 degree in those two polynomials. The other clue is that the higher powered function is inside the cosine function. Looking inside of a cosine function or inside of a sine function, inside of any trig function, is a good place to find wise choices for u. So both of those clues together point to u equals x cubed. So we're going to prepare to substitute. If u is x cubed, then du is 3x squared. We don't need the 3, so we're going to divide both sides by 3, and we're going to get 1/3 du. Based on our preparation work, we're going to regroup the integrand from x squared cosine of x cubed dx to cosine of x cubed multiplied by x squared dx. And then notice the kind of substitution that we can make. We're going to turn that x cubed into u, and we're going to turn that x squared dx into 1/3 du. This is an easier integrand. All we need to do is simplify it a little bit and then find an antiderivative. So this is the same thing as 1/3 cosine u du. And thinking about it, you probably don't even need to make this step if you're with it. That antiderivative is pretty easy. It's just 1/3 sine of u plus constant. And now that we have a antiderivative in terms of u, we just need to resubstitute to get a antiderivative in terms of x. So this gives me that the antiderivative is 1/3 sine of x cubed plus constant. So that is our substitution method. For important ideas, the substitution method is actually a way of undoing a chain rule. And so you got to think backwards from the chain rule. And your choice for U should be that first link in the chain. Okay. Remember that du has to be in the equation, and you have to turn everything into terms of U. Don't add variables, don't add constants or anything to make it match. You just got to use the substitution, the tools that you get through substitution, to make the integral match. If you need to multiply a constant to make things match, that's going to be okay. And the U-Substitution technique is strict. You have to match up U and du to x and dx strictly. And look for products where one factor is the derivative of an inside function. Inside of a trig function and the power of an exponential are also really good places to search for U. I'm going to highlight that because that's actually pretty important. Those are the places where we usually first look for our choices of U. So let's check our understanding. I think we have just one problem here. We've got the integral of 4x e to the x squared. And as we just said, we're going to look inside the exponential function for U. And we see that the exponent of e is x squared. Now the derivative of x squared is 2x. And I already have that x as one of the factors in the integrand. So it seems like it's going to be really easy to make this integral substitution and make things match. So let's start with u equals x squared. When you make the substitution, you usually go right from u equals x squared to du equals 2x dx. It's kind of a wasted step to write down du over dx equals 2x because you know where this is going already. So just go right to du equals 2x dx. And then let's take a look at the integrand and compare it to what we have. We already know about the x, and we already know about the dx. The other thing that we have there is a 4, and it would be really convenient if we can include that 4 into my du. Using algebra, it's not that difficult. We're just going to multiply both sides by 2. Now this is going to work really well because everything in the integrand is either going to be part of u or it's going to be part of du. 2du, that is. And you might be worried about the e, but that's not a worry because when you look at that, e to the x squared is just going to turn to e to the u, and you know what that antiderivative is. So let's make our substitutions. 4x e to the x squared dx. Now the 4x and the dx become 2du, and the x squared becomes u. Hopefully that color coding is going to kind of help you here. We're going to look at the resulting integrand, and we notice that everything is in terms of u. So we don't have to do any more simplification work. The antiderivative is 2e to the u plus constant. And substituting back in there for u, we get e to the x squared plus constant. And that's it. So this is going to be a really long journey for you into the substitution method. And like all the other methods we learned here, you are going to need a lot of practice here. Really, the experience is the only thing that's going to make this U-substitution easier for you. So don't be afraid of doing a little bit of extra work here and getting it done. This is not that difficult of a method. I don't think it is. Most of my students don't think it is. So you will get through this. You just need to practice. All right. See you, everyone.